Hi, welcome back. We've been talking about these functions of multiple variables, and last time we talked about how to draw a picture of the domain of a function. So now let's talk about sketching the graph of a function. So the graph of a function of multiple variables. All right, so if we're going to graph a function of multiple variables, then we have to think about what this the way we do graphs in the past, right? In the past, when we were doing graphs like a function y is equal to f of x, we might create a chart where we say, okay, x here, what's y, and then use that to plot some points on a graph, connect them, and that is our idea about what a graph was for a function of single variables. Now we're talking about a function that looks like z is equal to f of x, y. And in that case, you almost want to have a whole bunch of different examples of what x and y are, and that's going to give you z. So you plug in 0, 0, and you figure out what z is. You plug in 0, 1, you plug in 1, 0, you plug in 1, 1. You can see that this can get a bit more complicated, but the same idea works here in that what we're trying to do now, we have our three variables, we have our x, our y, and our z, is we see what we look at our different points here, the x, all the different xy pairs that are in our domain, and we figure out what the z value is at them. So, and we use that, we figure out what the z values are, and we use them, and we connect them, and we say, oh, this is now a surface that lies above the domain. So the domain lies in the xy plane, and the function, the graph, is a surface lying above the domain. Okay, and so this is really where there's a couple of things that we can draw, but in general it would be good to understand so these basic concepts, but then know how to get a computer to help us to graph these functions. So let's just do a couple of simple examples. So let's look at this f of xy is equal to 6 minus 3x minus 2y. Well, if we want to draw the graph of this function, one thing we might notice is that this looks like a very simple formula because it's only involving a functions of x, just multiples of x and multiples of y added together. And so this should feel like the answer is going to be something simple, just like a line in 2 dimensions. Well, this is going to be a plane in 3 dimensions. And we can see that even better if we write f of xy as a z, and we get z is equal to 6 minus 3x minus 2y, or 3x minus 2y, or sorry, 3x plus 2y plus z is equal to 6. And so we know this is the equation of a plane. So how are we going to draw it? Let's copy this over here. 3x plus 2y plus z is equal to 6 is a plane. So how might we draw a plane that in 3 space? So we draw our coordinates. one thing we can do is we can figure out, well, where does the plane intersect the x, y, and z axes? And so find where x, y, z, oops, sorry, find out where the plane intersects the x, y, z axes, and use and then use those points to help draw the plane. So in this case, if we're on the x-axis, then y and z are 0. So we get 3x plus 0 equals 6. So x equals 2. So we walk out 2 units, and this is our point that's on the plane. So this is 2, 0, 0. And then we look at what on the y-axis. We see that 2y is equal to 6, so y is equal to 3. So we walk out 3 units on the y-axis. And then z-axis, then x and y are 0, so z is equal to 6. And then we can basically connect these points and expand our plane. And that is one way to think about this graph of the R equation. So let's draw one more example. So one more example would look like g of xy is equal to the square root of 9 minus x squared minus y squared. So let's first think about the domain. The domain, we need that 9 minus x squared minus y squared is greater than or equal to 0. So this is something that says, okay, so x squared plus y squared is less than or equal to 9. And I hope that when you see this equation and you see x squared plus y squared equals 9, you're thinking, oh, that's a circle. And so x squared plus y squared less than or equal to 9 are points above this circle. So when we finally figure out what our equation, what our graph looks like, the domain of this function in the xy plane is going to be this circle. The domain of g. So whatever the graph is, it's going to be lying above that circle. All right, let's do one other. So we could start plugging in some points, right? We could plug in x equals 0, y equals 0. We get square root of 9. So this is 0, 0, 3 is a point. If we plugged in something like 1, 1, then we would get square root of 9 minus 1, square root of 7. So above here, this would be 1, 1, square root of 7. If we're over here, maybe at 2, 2, 0. So g of 2, 0 is equal to the square root of 9 minus 4 minus 0, so square root of 5. Okay, so you can see this is going to get rather tedious if you wanted to do all the points. So what do we have here? 2, 0, root 5. All right, well, let's try to do this a little bit more in a smart way, where we say, all right, this square root of 9 minus x squared minus y squared, if we wrote z equals that, z equals 9, square root of 9 minus x squared minus y squared, and then we took the square of both sides, So this is the same as z squared equals 9 minus x squared minus y squared. Then we would have x squared plus y squared plus z squared is equal to 9. All right, and we understood what x squared plus y squared is equal to 9 in 2 dimensions. And this came from the idea that what we have is we see that x squared plus y squared represents the square root of x squared plus y squared. This is the distance from 0, 0 to xy. And so square root of x squared plus y squared is equal to 3 is saying that we want all points that are a distance 3 from the origin. So when we take this equation and we maybe take the square root of it, this is something that we have seen. This is the distance from 0, 0, 0 to xyz. So the square root of x squared plus y squared plus z squared is a constant, corresponds to being, if you're in 3 dimensions, that's going to be the set of all points the same distance from the origin. That's going to be a sphere. Okay, so when you see an equation that looks like x squared plus y squared plus z squared is equal to r squared, this is a sphere of radius r. And so in terms of drawing this picture, then because we're dealing with maybe the top half, because this is the positive square root of 9 minus x squared minus y squared, then you get the top half of the sphere. So this is the graph of the top half of the sphere of radius 3. Oops. Oops. Why didn't that work? So this is a graph with the top half of sphere of radius 3. So before I go on to show us how to do this in Mathematica, what I think is really important to realize here is here we've been talking about function z is equal to f of x, y. And we've been saying, oh, that's a graph where we have some domain in the xy plane. In xy plane. And then it's a surface that is oriented in this z direction. So it's up, down, right? You can have a function like a negative function where the function lies below the xy plane. That's surely fine. But we might also rewrite our function. So if we had a function y is equal to g of xy, sorry, g of xz, where instead of z as a function of x and y, we have y as a function of x and z, then the picture is going to look different. This is sort of interchanging the roles of y and z, right? Remember, this is x, y, z, and in that case, the domain lies in the xz plane, and then the surface is oriented toward in the y direction. So in this case, the domain is in the xz plane, and the surface is oriented in the y direction. Right? And then there's one more way in which you could have a function. Right? So we could have a function that looks like x is equal to h of yz. Right? And in that case, then the domain is in this yz plane. And then the function gives you some surface lying up here in the x direction. So these would be considered explicit functions in which one variable is written explicitly as a function of the other variables. We're also used to maybe seeing functions that look like, so this is in comparison to implicitly defined functions, implicit functions. So this example, this x squared plus y squared plus z squared is equal to 9. This really isn't written where one variable is a function of another variable. Instead, you can think secretly, implicitly, that one variable is a function of the other variables. So this equation involving multiple variables can be understood as an implicit function in which each variable is implicitly, and I like to think of implicit being secretly, defined as a function of the other variables. And only sometimes is it possible to solve for one of the variables, for a variable. So only sometimes. So what I'd like to do now is I'd like to go over and show how to use Mathematica to plot functions and visualize domains, and not just for the functions we've been talking about, but also implicitly defined functions. So let's head over there. Here we are. So first thing, if we want to plot a function, let me make this a bit bigger. If we want to plot a function, so if we're plotting a function of one variable, we use the function plot. But if we want to plot a function of two variables, we use the function plot3d. What plot3d will do is you tell it what the function is in terms of the variables that you care about. So here we're looking for the square root of 16 minus x squared plus y squared. And you specify the values of x that you want to consider, the values of y that you want to consider, and I've put in some additional options here to make this easier to read. And when you use Shift Enter to evaluate, then you can see what the graph of this function looks like. Right, and you can see this is a function that's not defined over here or over here. It's only defined in this wider range. Right, so this, if we wanted to plot the function that we've been talking about, so plot of the square root of 9 minus x squared minus y squared, and we know we really only have to consider from -3 to 3 for x and y, then we can see that's the top half of the sphere. And the function's not defined outside because if you were to plug in some larger value, it wouldn't, the square root of that would be a square root of a negative number. So let's say we want to visualize the domain of our function. So this function above here, a good command to know for that is called the region plot. And what region plot does is you give it a set of inequalities, and you say, I want to find all points that satisfy those inequalities. So if you have one inequality, so what did we say up here? This was the square root of 16 minus x squared plus y squared. Well, we want to know when is 16 minus x squared plus y squared greater than or equal to 0. And you plot, you run that command, and this will tell you that, oh, the only points between -6 and 6 for x and -6 and 6 for y that work are those ones here in this region. We could make this bigger if we wanted to see what happens if our region gets bigger. And we can see that really this shape, what's happening is there's some hyperbola of points that are not allowed. If you wanted to specify multiple conditions, you can use and. You can use this double ampersand, and it will allow you to restrict not just by one equation, but also two equations. So this, if we had the restriction that x plus y has to be less than or equal to less than 2, then that's going to give us this shape for our region. And if we zoomed out again, what would that say? We zoom out again. Then this is what you can see, that this is what the region looks like as you zoom out further and further. All right, so let's stop there. And next time we're going to talk about understanding functions using their level curves. All right, see you.